Module 4, Section 3.2, Compound Interest and Continuous Compound Interest. Objectives. Objective 1, Understand and compute compound interest. Objective 2, Understand and compute continuous compound interest. Objective 3, Understand and compute annual percentage yield. And Objective 4, do some application problems. Objective 1, Compound interest. Unlike simple interest, compound interest on an amount accumulates at a faster rate. The basic idea is that after the first interest period, the amount of interest is added to the principal amount and then the interest is computed on this higher principal. The latest computed interest is then added to the increased principal and then interest is calculated again. This process is completed over a certain number of compounding periods. The result is a much faster growth of money than simple interest would yield. If at the end of payment period the interest due is reinvested at the same rate, then the interest as well as the original principal will earn interest during the next payment period. Interest paid on interest is reinvested is called compound interest. For example, suppose you deposit $1,000 in a bank that pays 8% compounded quarterly. How much will the bank owe you at the end of a year? Compounding quarterly means that earned interest is paid to your account at the end of each 3-month period, and that interest as well as the principal earns interest for the next quarter. Compound interest. This is the formula for calculating the compound interest. A is the amount at the end of n periods. I is the interest rate per period. You calculate it as R over M, where M is the number of compounding periods per year. T is the number of years, so we can calculate N, the number of compounding periods, as M multiplied with T. Notice that the rate per compounding period is found by dividing the annual rate by the number of compounding periods per year, and it is written as a decimal. Here are some examples. Given the annual interest rate and the compounding period, find I, the interest rate per compounding period. 17.3% compounded daily. So here we are going to assume that there are 360 days in a year. So to calculate the value for I, we divide the annual rate, which is 17.3%, by the number of days in a year, which is M value. So R converted as a decimal will be 0.173 divided by 360, getting the I value as 0.00048055. Second example, given the rate per compounding period, find the value for R, the annual rate. 0.875% per month. So there are 12 months and in a year, so therefore M value equal to 12. Given the value for I, which is 0.00875, I can substitute back in here I equal to R by M, or written as R equal to I times M. We get 0.105 or 10.5%. That is the annual rate. Find the amount to which 1500 will grow if compounded quarterly at 6.75% interest for 10 years. So we have the compound interest formula, amount equal to principal P multiplied with 1 plus R over M power MT. When we substitute the values, we get this expression, 1500 multiplied with 1 plus 0.0675 over 4 to the power 10 times 4. On calculation, we will get this as 2929.50. If we are putting this in the calculator, make sure that we use the appropriate parenthesis. This is how we do this in the calculator. 1500 multiplied with, then we need to start with a parenthesis, 1 plus 0.0675 divided with 4, and then you close the parenthesis, power key. Notice that 10 times 4 needs to be in the exponent. So we need to start another parenthesis here. Parenthesis 10 multiplied with 4 and close that parenthesis. If you press enter, we will get the answer 2929.50. Another example. What is the amount after 5 years if $1,000 is invested at 8% compounded? If the interest is compounded annually, m value equal to 1. So we can again substitute in the formula amount equal to P times 1 plus R over M power MT. Notice that M equal to 1, T equal to 5 years, rate is 8%, so we convert it back to 0.08. Answer for that will be 1469.33. If the interest is compounded semi-annually, that means every 6 months interest is added to the principal, M value will be 2. Amount equal to 1000 multiplied with 0.08 divided by 2. Notice that M value is substituted 2 over 2 times 5, 1480.24. Compounded quarterly means 4 times a year, so M equal to 4. Back in the formula, so we get 1485.95. Objective 2, continuous compound interest. Previously we indicated that increasing the number of compounding periods while keeping the interest rate, principal and time constant resulted in a somewhat higher compounded amount. What would happen to the amount if interest were compounded daily or every minute or every second? As the number m of compounding periods per year increases without bound, the compounded amount approaches a limiting value. This value is given by the following formula. The new formula is A equal to P multiplied with e to the power RT. This is the continuous compounding formula. Continuous compounded interest means that your principal is constantly earning interest and the interest keeps earning on the interest earned. So we have the continuous compounding formula here, A equal to P multiplied with e to the power RT. So we are going to do an example here. What amount will an account have after 10 years if 1500 is invested at an annual rate of 6.75% compounded continuously? So we need to use the formula A equal to P exponential RT. The value is given as 1500. Rate is the annual rate, which is 0.0675, 6.75%. T equal to 10. So we are going to put this in the calculator. So we do have 1500 multiplied with, now we need to call on this exponential function. So it will be second ln. So it will be e to the power. Then we need to put these two numbers within parentheses. 0.0675 multiplied with 10. And close the parenthesis. And then press enter. So we get 2946.05 rounded to 2 decimals. Finding the present value. How much should you invest now to have a given amount at a future date? So if you use the symbols, P is the present value, A is the future value or the amount accumulated. We are speaking about the value for P, assuming that A is given. So P is at the current time, A is at the future time. So we need to actually work with this formula. A equal to P multiplied with R by M power MT, and then solve for P in order to get the present value. So let's work out some examples. How much should you invest now at 10% to have 8,000 toward the purchase of a car in 5 years if interest is compounded quarterly and if interest is compounded continuously? In the first case, M equal to 4. The number of years will be 5. Rate is 0.10 given. And what we are getting here is the future value A. A is 8,000. We need to realize this amount for purchasing a car after 5 years. Substituting in the formula, A equal to P multiplied with 1 plus R by M power MT. I am interested in calculating P, the present value. So I can divide with the other factor, getting the new formula for P. P equal to A over 1 plus R by M power MT. Substitute the given values. A is 8,000 and so on. Now we can put this in the calculator to get 4,882.17. Let me show you that on the calculator too. So this is 4,882.17, again rounded to 2 decimals. If the interest is compounded continuously, we need to use the formula A equal to P e to the power RT. So that is calculated as, so that gives 4,852.25. Compute the growth time of an investment. The growth time of an investment is the time it takes for a given principal to grow to a particular amount. For example, how long will it take 10,000 to grow to 12,000 if it is invested at 9% compounded monthly, or if it is invested at 9% compounded continuously? Let's do this example. We have $10,000 invested that grows to $12,000 at a 9% rate compounded monthly. So we need to find the time value. So substituting up here, frequency is 12. Frequency means the number of interest conversions per year, 12. And the number of years is the unknown. So we need to solve this for t. We can divide with 10,000, getting 12,000 by 10,000, which is 1.2 on one side. 0.09 by 12. So if you do that, you will get 0.0075 added to 1. So this exponential equation is what we need to solve. Notice that the variable is in the exponent. To solve this one, we need to take the logarithms on both sides. Log 1.2 will be 12t multiplied with the log 1.0075. So keeping the variable t on one side, I can get log 1.2 divided with 12 times log 1.0075 as the value for t. In the second question, the compounding is continuously. So that means we need to use the formula A equal to P e to the power RT. So A is 12,000, P is 10,000, rate is 0.09. So this time we will get 0.09t equal to natural log of 1.2, taking logarithms on both sides. T equals log 1.2 divided by 0.09. Next objective is to compute the growth rate of an investment. If a $10,000 is invested in a growth fund, and if it has grown to $120,000 over a 10-year period, we are asking the question, what is the annual rate if the interest is compounded continuously? We need to look at the compounding. The compounding is continuously, so that means we need to use the appropriate formula. A equal to P multiplied with exponential RT. Substituting the values, we will get 12.6 equal to e to the power 10r. Again, taking the logarithms on both sides, I can write 10r equal to log 12.6. So the r value will be dividing with the 10. 0.25336 converted to percent, 25.34%. Next objective is to learn about annual percentage yield. The annual percentage yield, or APY, is the simple interest rate that would earn the same amount as the given annual rate for which interest is compounded. The APY is the rate actually earned or paid in 1 year, taking into account the effect of compounding. APY is also referred to as the effective rate or the true interest rate. Compound rates with the different compounding periods cannot be compared directly, but if we convert to APY, we can make that comparison easily. The formula for annual percentage yield. If a principal is invested at the annual rate R, compounded m times a year, then the annual percentage yield is given by this formula. APY equals 1 plus R by m to the power m minus 1. And if the interest rate is compounded continuously, then the annual percentage yield is given by the formula exponential r minus 1. Here are some examples. Find the annual percentage yield to the nominal rate of 7.4% compounded quarterly. So we substitute in the formula. Quarterly means 4. So we get 0.07607, which is 7.61%. So that means an annual rate of 7.61% is equivalent to 7.4% compounded quarterly. In the second example, the interest is compounded monthly, 1.12% compounded monthly. So that is comparable to an annual percentage yield of 1.13% approximately. Suppose we want to find the annual percentage yield for 13% compounded continuously. So this time the formula is exponential r minus 1. R is given as 0.13. So when we substitute this, we get 13.88%. Some application problems. As the price in a contest, you are offered 24,000 now or 44,300 in 6 years. If the money can be invested at 7% compounded annually, which will be worth more in 6 years? We are comparing two offers. Let's see what will 24,000 will grow to in 6 years. So we need to use the compound interest formula. 24,000 multiplied with annual rate is 7%, compounded annually means m value is 1. So when we substitute in the formula, we get 36,000 and 17.53. If we take the other offer, we will get 44,300. If the population of a country is growing at 2.3% compounded continuously, how long will it take the population to double? We need to take the population as the present value or the value. So if the population doubles, the value for A will become 2p. It is growing at 2.3% rate continuously. So that means R value is 0.023. Back to the continuous compounding formula, A equal to P e to the power RT. Substitute for A as 2p, that is doubling the population. Then we can divide with P. So we get this equation 2 equals e to the power 0.023 times t. So this is again an exponential equation we need to solve by taking the logarithms on both sides. Log 2 will be 0.023 times t. So t value will be log 2 divided by 0.023. That comes out to be 30.1368 years. Example 3. An IRA has 15,000 in it, and the owner decides not to put any more money into the account other than the interest earned at 4% compounded daily. How much will be in the account 41 years from now when the owner reaches retirement age? Here we are going to assume that an year contains 365 days. So we have P equals $15,000. Rate is given as 4%, which will be 0.04. Compounding is daily, so that means I need to take m value to be 365 and the number of years will be 41. What is the total amount after 41 years? So we need to substitute in the formula. A equals P multiplied with 1 plus rate by m power m times t. So I'm going to plug in the numbers. 15,000. I'm going to use the calculator now. So that means there will be $77,320.59 in the account after 41 years.